Dear students, welcome to the one-shot series of production engineering, and today we are going to discuss metrology. So all the important topics of metrology for GATE 2023 we are going to discuss today. Suppose some of you may be seeing this first time. So these are my credentials. I am gold medalist university topper for class 1997 from Aligarh Muslim University. I am MTech and PhD from IIT Delhi, and I am having 23 years of experience in teaching for competitive examinations. For 1.5 years, I worked as an IAS officer between 1999 and 2000. And I am basically a researcher. Primarily, I do research in material characterization and metal forming. And as per Scopus data, I am top 5% researcher in the world. This is our team. It is not effort of one person. We have a team of 13 or 14 people. So every person is an expert of his subject. Doesn't mean that one person is teaching everything, because one person cannot be expert of everything. So we have experts of practically every subject in mechanical. So now I'm starting metrology, one short course on metrology. We have to first of all understand that what was the need of metrology or industrial inspection. What was the need of metrology or industrial inspection? In production engineering, we say that we cannot duplicate anything. We cannot duplicate anything, because whatever is being produced, it is a final. Same product, it is not possible to duplicate. You know what is the reason? Some people say machine vibration, this and that. It's all wrong. The reason we cannot duplicate any product, because machine environment follows a normal distribution. Machine environment follows a normal distribution, and your normal distribution is like this. Normal distribution is like this, and X bar is called mean or mod, and it is also called targeted value. Targeted value. It is very, very important concept to understand in metrology, otherwise fundamentals will not be cleared. Suppose there is a hard automated lathe. This example practically I give in every class, because by this we can understand it. There is one hard automated lathe. You know what is a hard automation? Automation governed by 𝐂𝐴𝐴 follower arrangement is called hard automation. Automation governed by 𝐂𝐴𝐴 follower arrangement is a hard automation. Like in the first year of engineering, we go to machine shop. First year of engineering, we go to the machine shop. So no matter how hard you try, we are not able to machine, because we are students at that time. We are not able to do anything. After 2 days, we need to submit the job. Then we recall our non-teaching staff. Arey sir, can you make it for me? It happens with every student. It happened with me way back in 1993 at AMU. So non-teaching staff will come. He will adjust certain things, and the non-teaching staff will pull one lever. And the moment lever is pulled, tool is automatically moving towards the headstock. Tool is automatically moving towards the headstock at a constant speed without any human intervention. This is called hard automation. Because there is some cam and follower arrangement guiding this automation. So automation governed by cam and follower arrangement is called hard automation. So suppose there is a hard automated lathe targeted to produce shafts of 25 millimeter diameter. I have targeted to produce shafts of 25 millimeter diameter. In my book also, this is the example I stick to it. My book on production engineering, that is the example I stick to it. So, as the products are coming out of the machine, you are inspecting each and every shaft. If you do that, you will get dimensions like 25.023, 24.972, 24.996, 25.004. No two dimensions will match. No two dimensions will match, and there will be variation in the dimension. You know why? Because machine environment follows a normal distribution. And this is 3 sigma on this side, 3 sigma on this side, and within 6 sigma, there will be 99.73% component. Within 6 sigma, there will be 99.73% component. The sigma, the standard deviation depends upon the type of machine, number one. If it is a NC or CNC, sigma will be less. If it is a conventional machine, sigma will be more. Number two, standard deviation also depends upon the skill of operator. If the operator is highly skilled, sigma will be less. If the operator is a new person, sigma will be more. So all the machines, they follow a normal distribution. All the machines, they follow a normal distribution. So you cannot make anything exact. You cannot make anything exact because all the machines follow a normal distribution. All the machines follow a normal distribution. Because we cannot make anything exact, this fact that we cannot make anything exact, both producer and consumer knows. Now hear very carefully. This fact that I cannot make anything exact, both producer and consumer knows. That machine environment follows a normal distribution, so I cannot make anything exact. This fact both producer and consumer knows. So what consumer will say, what consumer will say that since you don't have capacity to produce component exactly, so as long as the components are coming in this range, it is acceptable to me. As long as the products are coming in this range, it is acceptable to me. This acceptable variation in the dimensions, this acceptable variation in the dimensions as specified by the consumer, acceptable variation in the dimensions as specified by the consumer is called desired tolerance. As specified by the consumer is called desired tolerance. So now tolerance word came into picture. Why we have to provide tolerances on the workpieces? Because we cannot make anything exact. Why we have to provide tolerances on the workpieces? Because we cannot make anything exact. So now there are two things. One is the desired tolerance. By the way, because these are recorded lectures going to you, if you have any question whatsoever, we have PW Telegram channel. If you see below that, their links will be given. So there's a Telegram channel where students can communicate with the teachers. So any question, you direct it to me, Dr. 𝐂𝐨𝐻, and I will take care of. So don't worry, we will provide all support, although it's a recorded one. If it is a live, I can see the chat and take care of the doubts there itself, but it's a recorded one. So any doubt you have, Dr. 𝐂𝐨𝐻, direct all the doubts to me for any medium. I will take care of, okay? So desired tolerances are given by the consumer, correct? And the second is the process capability. Process capability is nothing but 6 sigma. Sigma is the standard deviation of this normal distribution. 6 sigma. So the 6 sigma is the property of machine. This is the property of machine, and this is desire of consumer. Tolerances are selection of consumer, and the process capability is capacity of machine. If the machine is NC or CNC, 6 sigma will be low. And if the machine is conventional, 6 sigma will be more. I hope this is clear. So till now I have introduced a term called tolerances. And why the tolerances are provided on the component? Because we cannot make anything exact. So now this one-shot series is packed with the information, because generally when we teach in the live classes, because students are in front of us, so they ask doubt, we clarify, so many other things comes. But in the one-shot series here, concepts are one after another. Okay, that's the reason it is covered in the less time period. But anyway, students' queries will be taken care of. Okay. Suppose there are two machines. One machine producing whole. This is the normal distribution. And the machine producing shaft. This is the normal distribution. Machine producing whole and shaft, they will have different normal distribution. Suppose if it so happens that the process capability is equal to the desired tolerances. If it so happens that process capability is equal to the desired tolerances, it's rare, but suppose if it happens. that process capability of both the machines is equal to the desired tolerance. Suppose if it happens, then in that situation, there is no need of any inspection. There is no need of any inspection. So what I will do, machine producing hole, because this 6 sigma is equal to the desired tolerance for both the machines. No need of any inspection. Machine producing hole, put all these holes in the container. Machine producing shaft, put the shaft in that container. Now, randomly if you pick a hole, and randomly if you pick a shaft, random, because normal distribution means randomness. Randomly if you pick a hole from the hole lot, shaft from the shaft lot, assembly can be made. Without any inspection, assembly can be made. Assembly can be made. Okay? And this system is called full interchangeability. This system is called full interchangeability. So when the full interchangeability system will come? When the full interchangeability system will come? When desired tolerances are equal to the process capability. When the desired tolerances are equal to the process capability. Is that okay now? Now, what is a hole and what is a shaft? How to define a hole? Any internal feature of assembly, is called a hole, and any external feature is called a shaft. Any internal feature of assembly may not be circular, is called a hole, and any external feature may not be circular, is called a shaft. In 95% cases, we make the hole first, not the shaft. We make the hole first. It's a very frequently asked question in all the competitive examinations. In 95% cases, we make the hole first because standard sizes of drills and reamers are available. Because standard sizes of drills and reamers are available. That's the reason we make the hole first. And shaft is made to suit. So by the way, full interchangeability means there is no need of any inspection. Process capability is equal to the desired tolerance. So randomly pick a hole and pick a shaft, assembly can be made. Such systems are called fully interchangeable system. Such systems are called fully interchangeable system. Now the question is, what are the advantages of fully interchangeable system? There are three very, very important advantages of fully interchangeable system. Number one, holes and shafts can be made at different places where man and materials are cheap. Hole I will make it in Hyderabad, shaft I will make it in Delhi. Okay, wherever the man and materials are cheap. Correct, na? Another very, very important advantage of fully interchangeable system is standardization is possible. Another advantage is maintenance becomes cheap and easy. Maintenance becomes cheap and easy. How? Suppose there is an assembly and in this that assembly during service, shaft fails. Service shaft fails. You don't have to throw away the entire assembly. Purchase another shaft from the market and fit it. Maintenance becomes cheap and easy. You don't have to throw away the whole assembly. Purchase another shaft from the market and fit it. It will work. So we want a fully interchangeable system. We want fully interchangeable system, but in the real production scenario, we want fully interchangeable system, but in the real production scenario, process capabilities are more than the desired tolerances. Process capabilities are more than the desired tolerances. That is the reason I am not able to get fully interchangeable system. Why in the practical scenario I am not able to get fully interchangeable system? Because process capabilities are more than the desired tolerances. So now what to do? Now what to do? Let us take one example. Process capability is 4 times the desired tolerance. This particular example is taken practically in all the possible books. This example is taken practically in all the possible books. Process capability is 4 times the desired tolerance. Let us say, for example, then what I will do, I will divide the process capabilities. I will divide both the process capabilities into 4 equal parts. For whole, we designate it by capital letters, and for shaft, we designate by small letters. So process capability range I will divide into 4 equal parts. But practically how I will do? Over the board I have done it, but practically how I will do? Let us say desired tolerance is 0.1 mm and the process capability is 0.4 mm. Okay? Metrology lectures are highly packed, and unless and until you are from IITs and BITS, even the teachers are confused in metrology. So I will be happy when all of you are learning properly, and all of you should go to IIT or BITS once to see the culture of learning. There is no match. IITs and BITS Pilani, there are 3 campuses in India. There is no match to teaching in either. So most of you, those who are watching my lectures, maybe from private universities, whatever the university, doesn't matter. All of you at least once goes to these institutions to learn, to see the teaching culture. It will be a totally different experience because I spent a lot of time in IIT Delhi. So that's how I'm telling. Okay. So this is 25, 25.1, 25.2, 24.9, 24.8, and same thing here, 25.1, 25.2, 24.9, 24.8. So you know what I'm going to teach you now? What I'm going to teach you now, practically how you are going to break the process capability into 4 equal parts. Now, as the let us say shaft, as the shafts are coming out of the machine, as the shafts are coming out of the machine, I will inspect each and every shaft. I will inspect each and every shaft, and as per the dimension, I will place in the respective subgroup. I will place in the respective subgroup. I will have 4 drum A, drum B, drum C, and drum D. Let us say the dimension is 25.16. Put the shaft in drum D. If my dimension is 24.92, drum B. 24.89, drum A. Now, as the products are coming out of the machine, as the products are coming out of the machine, I will do 100% inspection. I will do 100% inspection. And as per the dimension, I will place the hole or shaft in the respective subgroup. If the if the process capabilities are worse than the desired tolerance, so what I will do, as the products are coming out of the machine, I will inspect each and every product. I will inspect each and every product, and as per the dimension, I will place in the respective subgroup. I hope this is clear to everyone. After producing, let us say, 1000 workpieces, after producing 1000 workpieces, each and every subgroup, here as well as here, each and every subgroup will have few pieces. Now, one more thing I would like to tell here. Whenever I use this term tolerance, whenever I use this term tolerance, I always refer to a group of components, not a single product. Tolerances are for a group of components, not a single product. Tolerance tells you that in this subgroup, what tolerance tells you that in this subgroup, this will be the variation in the dimensions of the product. What tolerance tells you? That this subgroup is having this much variation in the dimensions of the product. Okay. So now each and every subgroup will have few pieces. And the beauty is that in each and every subgroup, here very carefully what I am going to say, each and every subgroup, variation in the dimensions, each and every subgroup, variation in the dimensions are equal to the desired tolerance, By doing this procedure, each and every subgroup is having variation in the dimensions equal to the desired tolerance. So if you pick a shaft from subgroup small a, pick a shaft from subgroup small a, and if you pick a hole from subgroup capital A, pick up a shaft from subgroup small a, hole from subgroup capital A, assembly can be made. Assembly can be made. Why the assembly can be made? Because the dimensions are within the desired tolerance. If you pick up a shaft from subgroup small a, whole from subgroup capital A, because the variation and dimensions are equal to the desired tolerance, assembly can be made. These procedures are called selective assemblies. You must have heard this name. Selective assemblies. Selective assembly and full interchangeability. These are the topics in every syllabus of competitive examination. Selective assemblies and full interchangeability. So in other words, you can say that, you know what, I'm telling you the punchline. See, these definition you will not get in any book, because these things I have heard from my teacher in IIT Delhi, Professor 𝐂𝐤𝐴𝐻. Because I respect my teachers a lot, that's the reason I know funda. I don't claim basically that I am superhuman. I know funda because I respect my teachers both at IIT Delhi and Aligarh Muslim University. I used to have very excellent teachers. So Professor Tiwari, he taught me metrology, a very excellent teacher, Professor 𝐂𝐤𝐴𝐻. So it's a very, very important thing, because because it's a recorded one, I am not able to see your faces, all of your faces. Always remember, if you want to learn anything, respect teachers, respect parents, respect elders. If you disrespect them, immediately learning process is blocked. But one more question is there. Of course, parents we have to respect. Elders and teachers, if they have bad characters, because you know nowadays everybody can become teacher, it is driven by money, most of the cases. If they have a bad character, please do not respect them. Otherwise, bad character will go to your heart. If you respect by heart a person having bad character, those bad qualities will come to your heart. So please remember this very, very important thing. I teach students because I consider them as my children, and I really love all of you, because you will be seeing the recorded lectures. So this is a very, very important concept. Please follow. You will always be happy in the life. Many people are giving short lectures and all that, how to be happy. You cannot be happy unless and until you do this thing. Okay, very good. So I am telling you one punchline. Selective assemblies are the procedures. Selective assemblies are the procedures to achieve full interchangeability. Selective assemblies are procedures to achieve full interchangeability, even though machines are not capable. Even though machines are not capable, still I can achieve full interchangeability by the process of selective assemblies. Is that correct or no? Okay, all right. So next, just a minute, because I drink a lot of water. Because since childhood I have this habit of drinking a lot of water. It keeps our health in a better way. Okay. Let us say in any assembly you are using shaft from this subgroup. In any assembly you are using shaft from this subgroup. Because of some reason, let us say shaft fails. Because of some reason, let us say shaft fails. Then what you will do, you will go to market in Delhi. In Delhi, that hardware market is Chavdi Bazaar behind Jama Masjid, and in Hyderabad, it is Raniganj. I don't know which city you are in. Every city will have, industrial city will have hardware market. So if you go to market, you have to give three informations. You have to give three informations to the shopkeeper. You have to give three information to the shopkeeper. Only then he will pick the right product and give it to you. Because full interchangeability means maintenance becomes cheap and easy. Suppose I was using Shreshth from this subgroup and it fails. I have to go to market. I have to give three information. Then only shopkeeper will pick the correct product and give it to me. So what are those three information? See, in between I will give you some kind of, okay, okay. The three information is, first of all, you have to give the basic size. You know what is the basic size? Basic size is the targeted value, this one, targeted value for which holes and shafts are produced. And this targeted value is mod or median of normal distribution. Targeted value is mod or median of this normal distribution. Mod or median of this normal distribution. Mod or median of this normal distribution. So first information you have to give is the basic size. Second information that you have to give is, it's a very, very important topic, okay? Na? So when you are seeing this lecture, don't do too many things. Just look at the screen. If you are disturbed, you will not be able to follow, okay? Second thing is you have to give is this one. Desired tolerance. Desired tolerance. Desired tolerance is also called width of tolerance zone. Desired tolerance is also called width of tolerance zone. And the width of tolerance zone is also called grade of tolerance. It's also called grade of tolerance. All three are having the same meaning. So the second information that you have to give is, what is the grade of tolerance? Okay, everybody is okay? Is that okay with everyone? And third information that you have to give is, how far the tolerance zone is situated from the basic size. This distance. This is the basic size, is also called basic size. So how far tolerance zone is situated from the basic size? It is called fundamental deviation. It is called fundamental deviation. So what is the definition of fundamental deviation? What is the definition of fundamental deviation? Distance between the basic size and the limit closer to it. Or in other words, how far tolerance zone is situated from the basic size. How far? This tolerance zone is situated from the basic size. It's called fundamental deviation. Or fundamental deviation is the distance between zero line. What is the zero line? Basic size. Distance between the zero line and the limit closer to it is called the fundamental deviation. Okay? Is that okay with everyone? I hope everybody is okay. Everybody is okay on this? So, I have introduced these terms: basic size, desired tolerance, and the fundamental deviation. Okay? Where this normal distribution is situated, I want to magnify it now. This is called basic size. Basic size is also called zero line. Basic size is also called zero line. Now you have to see very, very carefully. Metrology, fundamentals are totally packed. In metrology, fundamentals are packed. So your normal distribution is here. See, it is like this. So dimensions are increasing in this direction. Dimensions are increasing in this direction. A, B, C, D. Because this is 25, na? This is 24.9, 24.8. So A is between 24.8 to 24.9. So it's a diameter of shaft, 25. So dimensions are increasing in this direction. So A will fall here. B, C, D. So if I take it out, this is the tolerance zone. This is the tolerance zone. Correct? This A I have taken out. This is the tolerance zone. Dimensions are increasing in this direction. Tolerance refers to a group of products. Tolerance refers to a group of products, not the individual product. Tolerance refers to a group of products, not the individual product. So what tolerance tells you that in this subgroup, this is the maximum size and this is the minimum size. In that subgroup, this is the maximum size and this is the minimum size. And this is also called upper limit, and this is called lower limit. Upper limit and lower limit. Now, what I recommend to you, especially in metrology and forming. In metrology and forming, what you should do, this one-shot lectures are around between 4 to 4.5 hours. You see in two parts. Because especially forming and metrology, if you see single part, whenever you're free, fumes will come out from your head. Because forming and metrology, they are not easy topics. If it is a live, I could have taken care of your doubts. So see in parts. That's my recommendation. But if you can digest, we are happy. This is called upper limit. This is called lower limit. This upper limit is also called 𝐂𝐤𝐡 superior. 𝐂𝐤𝐡 superior. E ES, and this is called 𝐂𝐤𝐡 inferior EI. Generally for whole shaft we use small letters, for hole we use capital letters. So suppose the tolerance is here, this is 𝐂𝐤𝐡 inferior, 𝐂𝐤𝐡 superior, and in this case this is the fundamental deviation, and here this is the fundamental deviation. So 10 minutes back what I told you, fundamental deviation is the distance between the zero line and the limit closer to it. It can be lower limit or it can be the upper limit. So whatever limit is closer to the zero line, that distance we take to quantify fundamental deviation. So fundamental deviation is the distance between zero line and the limit closer to it. It can be lower limit or it can be upper limit, depends upon where is our tolerance zone, below the zero line or above the zero line. Depends upon where is your tolerance zone, below the zero line or above the zero line. Okay. When the tolerances are only on one side, either like this or like this, it is called unilateral tolerances. When the tolerances are only on one side of the zero line, either this side or that side, it is called unilateral tolerances. But when the tolerances is spread, on both the sides of the zero line, like this, when the tolerances is spread on both the sides of the zero line, it is called bilateral tolerances. Bilateral tolerances. Practically, we prefer unilateral tolerances over bilateral tolerances. This question repeated many times in UPSC, civil services, forest services. There are many exams of UPSC. That why unilateral tolerances are preferred. Of course, you can give many arguments, but the most important argument in this is, if we follow unilateral tolerances, selective assemblies will be easier. Selective assemblies will be easier. That is the best argument we can give to choose unilateral tolerances. So when once again, tolerance means a group. Tolerance means a group, not the individual component. Okay? And when the tolerances is spread on both the sides of the zero line, it is called bilateral tolerance. Okay? Now, there is something called fit. Fit is called quality of assembly. Fit is called quality of assembly. In other words, relationship between hole and shaft, before assembly is called fit. Relationship between hole and shaft before assembly is called fit. Okay, and there are three types of fits. There are three types of fit. Of course, there are there are subcategories, and those who understand Hindi, these things I have covered in the crash course in detail. I have covered in the crash course in the detail. Suppose this is your hole tolerance of hole, and this is the tolerance of shaft. This is the zero line. Zero line is nothing but basic size. Zero line is nothing but the basic size. Dimensions increases in this direction. If you see the center line, this is the center line. So the dimensions will increase in this direction. 𝐂𝐤𝐻 inferior, 𝐂𝐤𝐻 superior. 𝐂𝐤𝐻 inferior, 𝐂𝐤𝐻 superior. We use capital letters for hole and small letters for shaft. So now if it so happens, now I will speak the sentences very, very slowly. If it so happens that in the subgroup of shaft, maximum size is smaller than the smallest size of hole. The maximum size of shaft is smaller than minimum size of hole. This fit is called clearance fit. Clearance fit. Minimum size of hole, maximum size of hole. Minimum size of shaft, maximum size of shaft. When the maximum size of shaft is smaller than the minimum size of hole, it is called clearance fit. And this is called minimum clearance. And this is called maximum clearance. Minimum clearance and maximum clearance. And understood what is a clearance fit? Now, based on my experience, students struggle to understand what is maximum material limit and allowance. So I will speak very slowly here. There is something called maximum material limit. Maximum material limit. Maximum material limit or minimum material limit. The dimension at which I'm explaining what is maximum material limit. The dimension at which hole or shaft, the dimension at which hole and shaft will have more weight. The dimension at which hole and shaft will have more weight is called maximum material limit. Is called maximum material limit. So I can say that upper limit of shaft will have more weight, and the lower limit of hole will have more weight in it. Lower limit of hole will have more weight, and upper limit of shaft will have more weight. So lower limit of hole and upper limit of shaft is called maximum material limit, and these are called minimum material limit. The limit at which, you just remember the sutra, the limit at which hole and shaft will have more weight, hole and shaft will have more weight, is called maximum material limit. It's a sutra. It will, it will always be correct. So now we define a term called allowance. Based on this, we define a term called allowance. You know what is allowance? Allowance is in any assembly of hole and shaft. Please hear very, very carefully. Allowance is in any assembly of hole and shaft, difference between the maximum material limit. Difference between the maximum material limit of hole and shaft is called allowance. Difference between the maximum material limit of hole and shaft is called allowance. Okay, so here for clearance fit, this is allowance. For clearance fit, allowance is equal to the minimum clearance. For clearance fit, allowance is equal to the minimum clearance. 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 Is equal to the minimum clearance. So this is a clearance fit. Clearance fit. Now let us say this is the hole and here is a shaft. Here is a shaft. When the minimum size of shaft is more than the maximum size of hole, it is called interference fit. And to make the assembly, we have to apply a force. To make the assembly, we have to apply a force, and this is called minimum interference. And this is called maximum interference. Maximum interference. And because our allowance definition will not change, maximum interference is called allowance. Definition of allowance will not change. What is the definition of allowance? Difference in the maximum material limit of hole and shaft is called allowance. Okay, na? Difference between the maximum material limit is called allowance, and allowance is equal to the maximum interference. Okay, so interference fit. Now suppose there is an overlap. Let us say this is the hole and this is the shaft. If there is an overlap in the tolerances of hole and shaft, if there is an overlap in the tolerances of hole and shaft, it is called transition. Ayo, kya ho gaya hai? It is called transition fit. It is called transition fit. If there is an overlap in the tolerances of hole and shaft, it is called transition fit. So broadly, there are three types of fit, but each fit is divided into 2-3 subcategories. So in the one shot, I am not going to the detail of that. In the crash course, I have covered. But one shot means between 4 to 4.5 hours, we have to cover all the important topics of the metrology and present it to you. That is the target of one shot. Okay. So there are basically only three types of fit: clearance fit, interference fit, and the transition fit. And the definition of allowance will not change. The definition of allowance is always the difference between the maximum material limit of hole and shaft. Okay? Now, there is something called fundamental deviation. We discussed what is fundamental deviation. And there is a grade of tolerance. Fundamental deviation and the grade of tolerance. Both fundamental deviation and grade of tolerances are standardized. Why the standardization was required? So that both consumer and producer can select from the available standard. Both consumer and producer select from the available standards. Select from the available standards. So this fundamental deviation the fundamental deviation is divided into 25 different subgroups. See, once again, some book says 26. Follow 𝐂𝐸𝐸. Metrology 𝐂𝐸𝐸 is a very, very good book. Metrology 𝐂𝐸𝐸 is a very good book. Other books, because it's going on record and it is freely available on YouTube, so I will not tell the names. Please don't follow any other book. There are hundreds of mistakes in that. If it is a app class or personal class, I could have told all the names. And there is a very popular book in private colleges. Please don't follow that. There are hundreds of mistakes in metrology. So, and unfortunately, many teachers teach from that book. IIT, nobody follows that. IIT, they follow 𝐂𝐸𝐸 and 𝐂𝐤𝐿. There is another book, 𝐂𝐤𝐿 and 𝐂𝐸𝐸. IITs, they follow these two books. Okay. So there are 25 different types of fundamental deviations. For holes, it goes like this. And for shafts, it goes like this. So both consumer and producer, they have to select from this available fundamental deviation. You cannot invent on your own. Otherwise, maintenance will be complicated. A, B, C, D, E, F, G. Some letters are missing and some letters are additional. Let us say A. For hole, we designate by capital letter. This is the fundamental deviation of type A. Okay, na? So A, B, C, D, E, F, G, H will be here. Some letters are missing and some letters are additional. Some letters are missing, some letters are additional. For H type of fundamental deviation, see very, very carefully. For H type of fundamental deviation, lower limit coincides over the zero line. Lower limit coincides over the zero line. Lower limit coincides over the zero line. So fundamental deviation is 0. So fundamental deviation is 0. For H type of hole, fundamental deviation is 0. In any assembly of hole and shaft, in any assembly of hole and shaft, if you are using H type of hole, it is called hole basis system. In any assembly of hole and shaft, if you are using hole from the H subgroup, it is called hole basis system. H, I is missing, J is missing, then JS. JS is bilateral. Out of 25, there is only one bilateral tolerance, JS. 𝐂𝐿𝐴 like P, ZA, ZB, ZC. ZB, ZA, ZB, ZC. Okay, that's how. For hole, fundamental deviation goes in this direction. For shaft, fundamental deviation will go like this. This is the A type of shaft. This is the fundamental deviation of A type. See, epsilon A is equals to epsilon small a. Only the sign will be different. This side it will be positive. This side it will be negative. Okay, quantity may be same, but above the zero line it is positive. Below the zero line it is negative. Okay, A, B, C, D, E, F, H will be here. For H type of hole, H type of shaft, small h type of shaft, upper limit coincides over the zero line. Upper limit coincides over the zero line. So the fundamental deviation will be 0. Fundamental deviation will be 0. Correct, na? In any assembly of hole and shaft, in any assembly of hole and shaft, if you are using shaft from this subgroup H, in any assembly of hole and shaft, if you are using shaft from this subgroup, it is called a shaft basis system. It is called shaft basis system. Now, some students ask a very technical question. Some students ask a very technical question. They ask, if you are using a hole from this subgroup, shaft from this subgroup, it is called hole basis system, shaft basis system. But suppose we have an assembly. Suppose we have an assembly in which you are using hole from this subgroup and shaft from this subgroup. Now, which basis it is? Technical question, huh? I am using hole from this subgroup and shaft from this subgroup. Now, which basis is it is? Still, we will call it as a hole basis system. Still, we will call it as a hole basis system because hole is my priority. Because hole is my priority. 95% cases, I make the hole first. I make the hole first. So hole is my priority. Still, I will call it as a hole basis system. Okay, na? Now, JS is bilateral. 𝐂𝐿𝐴 QRS TUV W X Y Z A Z Z A ZB and ZC. So the shaft goes in this direction and the hole goes in this direction. So as soon as the problem is given in the exam, This diagram should come to your mind. This diagram should come to your mind that where the tolerances are saturated. Where tolerances are saturated. Where the tolerances are saturated. Very, very important. You should know where the tolerances are saturated before attempting the solution of the question. Before attempting the solution of the question. Okay? So, what I have discussed with you is standardization of the fundamental deviation. Standardization of fundamental deviation. Now see grade of tolerance. Now see grade of tolerance. Grade of tolerance. As the basic size increases, it is difficult to provide closed tolerances. Let us say if you are saying 150 plus minus 0.003, technically it is not possible. Technically it is not possible. Closed tolerances cannot be provided when the basic size increases. So when people were standardizing the grade of tolerance, you know what they thought? They thought of varying the tolerances as per a cubical equation. They thought of varying the tolerances as per cubical equation. But when they propounded this theory, immediately there was a problem. Let us say for basic size 18, this is the tolerance. Let us say, I'm just taking a rough example. Basic size 18, this is the tolerance. And the moment basic size increases little bit, the moment basic size changes little bit, there was change in the tolerances. So then they came up with an idea. What is the idea? Let us have same tolerances. In a certain diameter range. And they standardized these diameters. From 0 to 3, have same tolerances. 3 to 6, 6 to 10, same tolerances. 10 to 18, 18 to 30. Let us have same tolerances. So in this range, have same tolerance. 0, 3, 6, 10, 18. Let us say this is the D1 and this is the D2. And this curve is passing through the geometric mean of these two. I mean, D is equals to under root D1, D2. The curve is passing through the geometric mean. That's the reason in your BTech you must have mucked up that in the y-axis it is called I. I is called fundamental tolerance. Fundamental tolerance. And the equation of this I is I is equals to 0.45 d raised to power 1 by 3 plus 0.001 d. This is the equation of this curve. So in your BTech you must have studied that we take the geometric mean diameter, basic size, in what range it is there, but we never understood why we are doing this. We are calculating the geometric mean because my tolerance curve, fundamental tolerance curve, is going through the geometric mean. Fundamental tolerance curve is going through the geometric mean. So that is the reason I take the mean, and this is the equation. Everybody understood now? Kindly note that this is in microns and this D is in millimeter. Input to this D will be in millimeter, but output will be in microns. Many students do mistakes here. So when people were developing this system, every tolerance was integer multiple of I. Integer multiple of I. Every tolerance was integer multiple of I. That's the reason I is called a fundamental tolerance. Once again, I'm telling you, those who are studying first time, it will be too much for them. That's the reason they should see this lecture in parts. This particular lecture, metal forming and metrology. Because in private colleges, they don't teach anything, because I know this thing very well. So if it is too much for you, again see. Okay, now because I'm not able to see that, your queries. So every tolerance was integer multiple of I. So these tolerances initially were divided into 16 grades. IT1, IT2. IT stands for international tolerances. IT stands for international tolerances. IT4, IT5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So originally, here very carefully, originally it was divided into 16 grades, and IT1 was I. We have calculated I before. And these tolerances were arranged. These tolerances were arranged in 5-step preferred series. 5-step preferred series. 5-step preferred series. 5-step means it's a modified geometric series with geometric ratio 10 raised to power 1 by 5. 5-step means 5th step will multiply by 10. Every 5th step will multiply by 10. So 1, 2, 3, 4, 5, 10i. 1, 2, 3, 4, 5, 100i. 1, 2, 3, 4, 5, 1000i. So every fifth step will multiply by 10, and it's a modified geometric series. I will explain to you what is the meaning. Modified geometric series is called preferred series. This is 10i, so this will be 10 raised to power 4 by 5i. This will be 10 raised to power 1 by 5i. Correct, na? So you know what we do? Why it is called preferred series? Why it is called preferred series? If you solve it, you make it an integer. Sometime lower, sometime higher. I am not following any rule. Sometime I will select the lower integer, sometime I will select the higher integer. I will not follow any rule. That is the reason it is called a preferred series. I am not following any rule. That is the reason it is called preferred series. 16i and so on. So all these 16 tolerances were arranged in a 5-step preferred series. Fifth step will multiply by 10 geometric series. Whatever comes out after calculation, I will round off. Sometime lower, sometime higher. Okay, na? But later on, slip gauges, sine bars were invented. Slip gauges, sine bars, angle blocks, precision balls, they were invented. So people wanted 2 more precise grades, precise than IT1. So they have introduced IT0 and IT01, similar to the 0th law of thermodynamics. First law of thermodynamics came first. 0th law was invented later, but it should have come before first law. That's the reason they called it 0th law. Same thing here. Now IT1, they don't follow I. IT01 to IT1, they have given empirical formulas. From IT01 to IT1, they have given empirical formulas. So there are 18 grade of tolerances. There are 18 grade of tolerances. So both consumer and producer, they have to select grade of tolerance out of these 18 and fundamental deviation out of those 25. Both producer and consumer, they have to select from the available standards. They have to select from the available standards. Otherwise, maintenance will be a problem. Otherwise, maintenance will be a problem. Correct? Otherwise, maintenance will be a problem if you don't follow the standards. Okay? So now, something like this is given to you, 25 H7 D8. In exam, please remember, before solving problem of limit, fit and tolerances, before solving the problem of limit, fits and tolerances, you have to make the fit diagram. And what is a fit diagram? I am going to explain to you. What is a fit diagram? I am going to explain to you. This is called basic size. Whatever is written in the capital letter, it is the information about whole. And whatever is written in small letters, it is the information about shaft. So I am making the fit diagram now. 25 is the size of hole. So whatever type of question is given to you in any exam, no matter how simple it looks like, no matter how simple it looks like, you should always make a fit diagram first. You should always make a fit diagram first. So H type of hole, where it is appearing, it's a hole, it's a H type. See the fundamental deviations that we discussed half an hour back. 7 means this is IT7. IT7 width of tolerance zone will be given to you. So this is IT7. D shaft, A, B, C, D, E, F, G, H. So D will be somewhere here. This is the fundamental deviation of D type. 8 means this is IT8. This is your shaft. So this is the fit diagram of this information. So we can see from here it is a clearance fit. It's a clearance fit. So once again, please remember, while attempting the questions of limits, fits and tolerances, please remember to make the fit diagram first. Please make the fit diagram first before answering. Please make the fit diagram first before answering. Otherwise, there will be a problem. There will be a problem. Okay? All right? We are going to solve some problem after maybe half an hour to see some sample problems. Suppose this is your raw material, 200 millimeter length, and the 60 millimeter diameter. This is your raw material. This is your raw material. And from this, I want to produce this geometry. 40, 50, 100, 35. I want to produce this geometry. Please see very, very carefully. There are some technicalities involved here. Okay. So initially what you did, you have loaded the material over a milling machine. You have loaded the material over a milling machine, and with the help of end milling cutter, you are turning. With the help of end milling cutter, you are turning. And the moment the diameter becomes 50, you are taking this as reference, measure 40 millimeter in the machine and apply a cut. You are measuring 40 millimeter in the machine and applying a cut. In metrology, what we learned, we cannot make anything exact. We cannot make anything exact. So you cannot measure exactly 40. You cannot measure exactly 40. So process capability of machine will appear as tolerance in this section. Process capability of machine will appear as tolerance in this section. Let us say 40 plus minus 0.04. Process capability of the milling machine will appear as tolerance in this section. Okay. Now what you did, you have taken out the semi-finished specimen from the milling machine and put it over a lathe machine. Put it over a lathe machine. And with the help of a single point cutting tool, you are turning this section. With the help of a single point cutting tool, you are turning this section. And once it becomes 35, you are taking this as reference, measure 140, and cut off from here. Cut off from here. So 140. The process capability of lathe will appear as tolerance in this section. Let us say this is plus minus 0.07. Plus minus 0.07. Okay. Now the question is, what will be the tolerance of this section? This is called a sink. This is called a sink. So the answer is, tolerance always add. Because it's a one-shot course, I am not telling too many things because otherwise it will be 20 hours course. We will take only the selected problems. And if you want to see the variety and more problems, see our Abhyas batch. There I have discussed very, very good problems from all these, whatever I am teaching you. Abhyas batch, it is in English, because primarily these English batches are recorded for the English, I mean those students who do not understand English or Hindi, like South Indian students on northeastern part. So if you want to see many, many problems, see our Abhyas batch, that is in English. And I have done a lot of problems there. So this is the sink part. Tolerance will always add 0.07 and 0.04, 0.11. It will add. Tolerance will always add up. Tolerance will always add up. And this part is called a sink. In our crash course and Abhyas, we have done many, many problems. Here I will see only the selected problems. Okay, na? So sink. In exam, whatever is the unknown is a sink. Whatever is the unknown is a sink. Okay? Whatever is the unknown is a sink. Till now, what we have discussed, limits, fits, and tolerances. Till now, we have discussed limits, fits, and tolerances. Limits, fits, and tolerances. And what is our conclusion? you cannot make anything exact. You cannot make anything exact. That is our conclusion. You cannot make anything exact. So tolerances. Both hole and shafts will be in the tolerances. Now the question comes, who will check? Who will check whether holes and shafts are coming within the tolerances? Who will check? Who will certify me that this group of hole is within the tolerance, this group of shaft is within the tolerance? Who will certify? Those things are called limit gauges. Limit gauges. Limit gauges will certify that these holes and shafts are coming within the tolerances. Now for hole, we use plug gauges. Plug gauges are like this. It's a handle. Plug gauges are like this. And for shafts, we use ring gauges. And the ring gauges are like this. And we are carrying out inspection of shaft like this. For shafts, we use ring gauges. For holes, we use plug gauges. Now, both the gauges are of two types. One is a go, another is a not go. See, it is a convention that we use only capital letters. It is a convention that we use only capital letters. Okay, na? These limit gauges are designed as per Taylor's principle. Limit gauges are designed as per Taylor's principle. Limit gauges are designed as per Taylor's principle. Taylor is a very popular personality in mechanical engineering. So what is the Taylor's principle? This Taylor given two statements. Let us say this is the hole, and this is the shaft. So plug gauges I will design here, and the ring gauges I will design here. Taylor given two principles. So first statement of Taylor. First statement of Taylor. Taylor said, go gauges are designed for maximum material limit condition. Go gauges are designed for maximum material limit condition, and the no-go gauges are designed at minimum material limit condition. No-go gauges are designed at minimum material limit condition, meaning for plug gauge, this will be the size of go, and this will be the size of no-go. For ring gauge, this will be the size of go, and this will be the size of not go. Okay? For plug, this is the size of go, no go. Ring, this is the size of go, this is the size of no go. Okay, I have shown you the geometry, how the plug gauges looks like and how the ring gauges looks like. So when the go gauge goes inside the hole, when the go gauge goes inside the hole, it means the size of hole is greater than the size of GO gauge. If the GO gauge goes inside the hole, it means the size of GO gauge, size of hole is greater than the size of GO gauge. And when the no GO gauge doesn't go, it means the size of hole is less than the size of no GO gauge. So when the GO gauge goes and the no GO gauge doesn't go, GO gauge goes and the no GO gauge doesn't go, it means my hole is in the correct tolerances. When the GO gauge goes and no GO gauge doesn't go, it means my hole is in the correct tolerances. Okay? Correct, na? But suppose GO gauge doesn't go. Suppose the GO gauge doesn't go, it means the hole is undersized. It means the hole is undersized. And if no GO gauge also goes inside the hole, if the no GO gauge also goes inside the hole, it means the hole is oversized. It means the hole is oversized. It means the hole is oversized. Correct? Same thing for ring. Same thing will happen for the ring. Correct, na? And when the GO and no GO are mounted on a common handle, this is the GO part, this is the no GO part, and this is the handle. When the GO and no GO are mounted on a common handle, these gauges are called snap gauges. When the GO and no GO are mounted on a common handle, these gauges are called snap gauges. These gauges are called snap gauges. Okay? So same thing for GO and no GO ring. Whatever we discussed, there is a problem. You know what is the problem? What I'm saying that size of GO gauge is here and size of no GO gauge is here. But the foundation of metrology is I cannot make anything exact. Foundation of metrology is that I cannot make anything exact. So there will be tolerance on the gauges. There will be tolerance on the gauges. Gauge tolerance is equals to 1/10 of the work tolerance. Gauge tolerance is equals to 1/10 of the work tolerance. What is the work tolerance? If you are designing plug gauges, X is the work tolerance. If you are designing plug gauges, X is the work tolerance. And if you are designing ring gauges, Y is the work tolerance. If you are designing ring gauges, Y is the work tolerance. And if you are designing plug gauges, X is the work tolerance. Correct? Now there is an issue. To measure the tolerances of hole and shaft, I brought gauges. Now you are saying that there will be tolerance on the gauges. Who will measure the tolerance on the gauges? Optical flat. Optical flat is like a god. Like in this world, when all the hopes fade, suppose somebody is sick, when all hope fades that he is not going to survive, then the family member says, oh my God, do something. Correct, na? So God is our last hope. Similarly, in metrology, when all the inspection procedure fails, we remember optical flat, because whatever inspection nobody can do, optical flat can do. So who will measure the gauge tolerances? Optical flat. So this is the first principle of Taylor. Now the second principle of Taylor. Second principle of Taylor. Second principle of Taylor is go gauges are designed to check size as well as shape, and it has to be in the full form. Size as well as shape, and it has to be in the full form, means full working length. I will give you some example of that. Suppose this is your hole. Suppose this is your hole. Length of go gauge will be like this. See. The length of go gauge should be such that it covers the entire working length of the hole, because it is supposed to check the size as well as shape. Suppose there is a taper, it will be catched by the go gauge. There is one question that appeared in GATE, and this question keeps on repeating in many PSEs and all that. Go gauge, size, shape, A, B, C, D, like this. So many teachers also, they say, no, its shape is not correct. They are wrong. It check the shape. So because go gauge every time it is moving inside and outside, go gauge every time moving inside and outside, so there will be wear on the go gauge. There will be wear on the go gauge. Not a no, because no go gauge doesn't cover the entire working length. So there will be wear on the go gauge. So we provide wear allowance on the go gauge, and it is 1/10 of gauge tolerance, or 1/100th of work tolerance. Wear allowance will be given only on the go gauge. Please remember one thing. When the work tolerance is less than 0.1 mm, wear allowance will be 0.001. Correct, na? So almost 1 micron. It is very difficult to provide. So when the work tolerance is less than 0.1 mm, we do not provide any wear allowance. So this is the second principle of Taylor, that go gauges are used to check size as well as shape. And no go gauges are used to check one element at a time. No go gauges are used to check one element at a time. Now, what is the meaning of one element at a time? Suppose there is a hole. And while machining this hole, due to inaccuracies, somehow this hole is oval. The ovality is such that you are not able to see from your naked eyes. Ovality is such that you are not able to see from your naked eyes. So how to check? By no-go gauge. No-go gauge will be like a dumbbell. No-go gauge will be like a dumbbell. So keep it at different locations. Keep it at different location. Put it here. Not going. Put it like this. Not going. Put it like this. Not going. But if you put it like this, it will go. If you put it like this, it will go. Keep the no-go gauge as a multiple location. Here, 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 multiple location. And at one location, if it goes, it means the hole is oval. That's the meaning of. That is the meaning of one element at a time. That is the meaning of one element at a time. Okay? Okay? Is that all right? Gauge design. So here I will not get into too much detail. Here I will not get into too much detail because I am not see you face to face, or chat is also not live. Because if there is any confusion, there will be a problem for you. So I will explain to you, but I will not get into too much detail. But on the gauge design, there is one lecture of mine on YouTube that you can see. It is around 45-minute lecture just on the gauge design. Whatever I'm going to speak for 5 minutes, it is around 45-minute lecture, elaborate. So that you can see on the YouTube. Suppose this is the hole and here is a shaft. Once again, I am only giving you the result here. Only I am giving you the result because the things are a little complicated. If you want to study this further, for this 5-minute teaching, I have 45-minute lecture on the YouTube. Just search gauge design 𝐂𝐨𝐻𝐿. You will get it, and it's in English. Okay, that also lecture is in English. Okay. So my plug gauges will be here, and the ring gauges will be here. My Taylor's principle says this is the go, no go, go, no go. This is X, this is Y. Y is the work tolerance of shaft and X is the work tolerance of hole. Okay. Primarily, I am teaching you here how you should handle the questions in exam. How you should handle the questions in exam. Okay. There are 3 types of gauges. First is a workshop type gauge. Once again, I am not getting into the nitty-gritty details because for some of you, fumes will come out. For that, if you want to study a little deep, my lecture on the YouTube. For workshop type gauge, tolerance will be towards the work tolerance. Tolerance will be towards the work tolerance. No go. Go. Go na? So this is x by 10, x by 10, and this is the VR allowance, x by 100. This is the VR allowance, x by 100. And for ring, this is the go. Go na? This is the no go. This is y by 10, y by 10, and this will be y by 100, y by 100. Okay na? So workshop gauges, tolerances will be towards the work tolerance. Tolerance will be towards the work tolerance. In the exam, whenever they say, design means you have to give the minimum and maximum value. Design means you have to give the minimum and maximum value. Okay. Now, second is the inspection type of gauges. Second is the inspection type gauges. In inspection type gauges, gauge tolerance is away from the work tolerance. Gauge tolerance is away from the work tolerance like this. Gauge tolerance is away from the work tolerance. This is ring. If you see carefully, on the inspection type gauges, I have not provided the wear allowance. The reason is, inspection type gauges are already slightly inaccurate. And if you provide wear allowance, it will make them more inaccurate. If you provide the wear allowance, it will make you more inaccurate. It will make you more inaccurate. All these discussions you will find in the detailed lecture. Now, there is something called ISO gauge. ISO gauge is also called general purpose gauge. ISO gauge is also called general purpose gauge. ISO gauge is also called general purpose gauge. It's not a new type of gauge. In ISO gauge, you take go from the workshop and the no go from the inspection. You take go from the workshop and no go from the inspection. Go from the workshop and the no go from the inspection. Go from the workshop and the no go from the inspection. No go from the inspection. So once again, these are the one-shot crash discussion. That's the reason, I don't want to, because I am not physically taking care of it out. I am not going very deep into it. But in the normal class, when we have sufficient time, we dive into it. Okay. So that was the theory. And I hope everybody digested. Everybody digested the theory. Everybody registered the theory? So let us discuss the questions. Let us discuss the question. I will go the same way. I will wait for some time, because if I directly give the answer, what is the fun? If I directly give the answer, what is the fun? And I also told you to make the fit diagram before hitting the answer. To make the fit diagram before hitting the answer. A hole is a dimension. Make the fit diagram first. Okay? This one. Both are positive. Here is this. Kindly remember the trick. You have to make the fit diagram before concluding anything. So, because both the tolerances are overlapping, so it's a transition fit. Both the tolerances are overlapping, so it's a transition fit. Correct, na? Both the tolerances are overlapping, so it's a transition fit. Once again, please remember this trick. For limits, fits, and tolerances, before attempting the answer of the question, you have to draw the fit diagram. You have to draw the fit diagram. Yeah, read the question first. Read the question first. I will give you some opportunity. Okay, 30-second break so that you can do on your own. Whole. Lower limit is 0.02. Upper limit is 0.04. Okay, na? So this is the whole. Shaft. Oh. Upper, see, this is 0.02 and this is 0.005. If you do that, the question is going to be very, very easy. The minimum clearance. This is the minimum clearance. B. Questions are easy. Questions are easy. But you should know the trick how to handle. You should know the trick how to handle. Questions are extremely easy. Questions are very, very easy, but you should know the trick. Correct? If you have If you are a little slow than me, you can pause the video and do the question. You can pause the video and do the questions. That is also all right. That is also all right. Okay. A shaft of diameter and a hole of diameter. First of all, shaft. 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 And the hole is here. Construction should be correct. Minimum is 0.01 and the maximum is 0.2. No, it's a point, sorry. 0.1. So now see, hole is here. So it's a clearance fit. It's a clearance fit. I hope it is okay for all of you. It's a hole and the shaft is this is a shaft. Now let us see what the question is asking. Hole and the shaft tolerances. So hole tolerance is 0.025 and the shaft tolerance is 0.08 minus 0.005. So it will be 0.075. This is 0.075 now. And because both the tolerances are overlapping, it's a transition fit. Because both the tolerances are overlapping, so it's a transition fit. Questions are easy, but suppose some theoretical question appears, that you have to be a bit careful about it. If theoretical question appears, you have to be a bit careful about it. Okay. Same thing here. Hole. Check, is that okay? I am standing on the side so that you can see the full screen. So that you can see the full screen. and the shaft is here. See, this is a shaft. So the basic size here is 25, na? Basic size is 25. Tolerance of shaft and hole. This is the tolerance of hole. This is the tolerance of shaft. Maximum and minimum clearances. Minimum clearance is 0.006. And the maximum clearance will be this. How much it is? 0.02 plus 0.03. 0.03 plus 0.02. So 0.05 is the maximum minimum clearance. Maximum material limit of hole and shaft. So the limit at which the material is more is called maximum material limit. So this 25 millimeter is the maximum material limit for hole. And this is the maximum material limit of shaft. How much it is? 25 minus 0.006 comes out to be 24.994 yum is the maximum material limit of shaft. So if you have a cool head, these questions are very, very easy. Okay. Look at the problem first. Oh. Look at the problem first. The tolerance of hole and shaft assembly having a nominal size of nominal and basic size is same for you are as follows. Make the fit diagram. That will be very, very easy for you after that. It's a hole. It's a 0.021. So your fit diagram is ready. Your fit diagram is ready. Maximum and minimum clearance. Minimum clearance is 0.04. Maximum clearance is 0.021 plus 0.075. 0.096, correct, na? This plus the whole thing. Allowance, it's a clearance fit. So clearance fit, minimum clearance is the allowance. In the clearance fit, minimum clearance is the allowance. And in the interference, maximum interference is the allowance. Maximum material limit of hole and shaft. Hole it is 40. Shaft it is 40 minus 0.04 comes out to be 39.96. Type of fit, it's a clearance fit. Type of fit, it is a clearance fit. Type of fit, it is clearance fit. Type of fit, it is clearance fit. So now read the question. A clearance fit has to be provided for a shaft and a bearing assembly. Bearing means you can say it's a hole. Bearing means it's a hole having a diameter of 40 mm. The tolerances on hole and shaft are, so tolerance of hole, this is your hole tolerance, and this is your shaft tolerance. The tolerances are disposed unilaterally. If an allowance of 0.006 millimeter is provided, find the limit size of hole and shaft when hole basis system and the shaft basis system. So let us try hole basis system. Fit is a clearance fit. So such type of question appeared many times in UPSC and once in GATE. So hole basis system means this is your hole, and hole tolerance is given 0.006. It's a clearance fit. So shaft will be like here. Shaft tolerance is 0.004. Shaft tolerance is 0.004. Allowance is 0.002. So it's a clearance fit. So allowance is equal to the minimum clearance. Now this is the fit diagram. Just look at it whether I have done correctly or no. Just look at it. Whether I have done it correctly. Limits and size of a hole and shaft. Okay. So the hole, maximum size, minimum size. Basic size is given to you. No, basic size is not given. So you have to 40 millimeter. So this is the minimum size. This is the maximum size. So 40. Maximum size is 40.006. Shaft, maximum size and minimum size. Maximum size is 40 minus 0.002, 39.998, and reduce 0.004 further, so 39.994. That is the answer for A. Similarly for B it can be done. So all these questions, if you keep your head cool, everything is easy. If you can keep your head cool, it's very easy. See the next question. See the next question. Find the limit size tolerances and allowance for a 100 millimeter diameter shaft and hole pair designated by F8 H10. Specify the type of fit that the above pair belongs to. Given 100 millimeter diameter lies in the range. So D will be under root 18 to 120. I told you know why we calculate the geometric mean? Because my curve is passing through the geometric mean. and I is 0.545 d raised to power 1 by 3 plus 0.001 d. Input to d in millimeter and output will be in microns. And fundamental deviation of F type is minus 5.5 d raised to power 0.41 microns. And for IT8, IT10, it is given 25I and 16I. Okay. So F8H10, you know what is the meaning of that? 100. This is the whole. A, B, C, D, E, F, G, H, I. And this is the fundamental deviation of F type. And H is here. A small means shaft. It's a hole. And this will be IT8. And this will be IT10. So all the values are given. Calculate I. This value is also given. This value is also given. Epsilon F formula is given. Calculate the numerical values and you will get the answer. Similar to the previous questions that we have done. So anyway, that's the reason, purposefully, because it's a one-shot course, I want to focus more on fundamental. That's the reason I'm not going too much into certain things. Question number 9. Question number 9. Okay. A small bore is designated as 25S7, IT7, and it's a whole 25. The lower and the upper limits of bore are 0.021. And when it's IT7, it is 0.021. When it is IT8, it is 0.033. And when the bore is designated as IT6, then the upper maximum limit, I mean, your question is asking about the tolerance zone. So you can have the iteration. Because it's a 5-step preferred series, na? That's what I taught you, 5-step preferred series. So by iteration, you will find it's a D answer. You can solve it. Because if it is, yeah, 10th question. 10th question, please. Read the question. I will give you break for 30 seconds. Okay. Okay. In GATE exam, please remember, there will be questions and the questions appears big, but the solution will be very short. It's a H type, na? And H type fundamental deviation is 0. H type fundamental deviation is 0. So in GATE, I have seen many times, especially in the metrology question, that the question appears big, but answer will be very short. So please don't get into solution. First of all, see the options. First of all, see the option. A 30 millimeter hole shaft assembly results in minimum and maximum clearances. The hole has a unilateral tolerance with 0 fundamental deviation. If the tolerance of the shaft is 0.0, it's a clearance fit. See, what are the values given? This is 0.03. This is 0.3. If the tolerance on the shaft is 0.08, find out this X. Find out this X. So, can I say 0.3 minus 0.03 minus 0.08? Can I do that? Can I do that? So upper limit is nothing but 30 plus tolerance. See, as I told you, if you see carefully, no matter how the simple problem looks like, I'm making the fit diagram first. Before solving, I'm making the fit diagram first. Okay, so you also please do the same thing. Please go through the problem. In a shaft hole system, the dimensions with tolerances are as follows. This is the shaft and this is the hole. When both x and y are positive real numbers, whichever of the following will provide an interference fit? It should be interference fit. Your shaft is a bilateral tolerance. Your shaft is a bilateral tolerance. It should be interference fit. It's a shaft. It will be interference fit only when a hole comes here. It will be interference fit only when the hole comes here. And hole, this is 0.03 and this is y. So it will be interference fit only when x is less than 0.03. It will be interference fit only when x is less than 0.03. And out of the given option, only D option is there in which x is less than 0.3. So this will be my answer. X is less than 0.03, so this will be my answer. Easy question, na? Okay. A cylindrical pin of diameter is assembled into a hole of diameter. Here this question is a new question. While handling the question, please make sure that the basic size is same. Make sure that the basic size is same. So make the basic size same. 1.996 0.0015 0.0015. To make it 2, it should be jumped by 0.004. Correct, na? Then it becomes 2. The remaining upper limit is 0.0015 minus 0.004. 0.00. No, actually we heard 000, na? This is 1.996. Okay, and then my tolerances are like this. This is 0.0015. This is 0.0015. Now to make it 2 minus 1.996 comes out to be 0.004. So what you do, you shift by 0.004, then it becomes 2. Now this becomes lower limit and this becomes upper limit. Okay, na? All right, na? So 0.004 minus 0.0015. So this will become 0.0035. 25 or so, 25, because 0.00004 minus 0.0015. 5.225. Okay, that way we will do that. Now similarly upper and lower limit can be calculated and then proceed with the solution. So here why I have introduced this this particular question is, for hole and shaft, if the basic sizes are different, you have to change the basic size in such a way that this also becomes 2. Basic size should be uniform, and the answer, if you calculate, answer will be A. In one shot, basically, I am not discussing too much, otherwise it will take 20 hours just in metrology. All right, so anyway, as I told you, some of the lectures are available. This is the gate question P by Q. This is the gate P by Q. What are the upper and lower limit of shaft? Shaft is 60 F8. So this is the question. Appears that we have to do a lot of calculation, but you don't have to do even a single calculation. 60 F is appearing like this, epsilon F. If you see the options, According to this fit diagram, both lower and upper limit should be less than 60. Both upper and lower limit should be less than 60, and this is thing there only in one option. See here, there's a 60, cannot be. More than 60, cannot be. More than 60, cannot be. So only option is A. So as I told you that in GATE sometimes the question appears that you don't have to even solve. So be careful about that. So this is the question. This is the question. A cylindrical pin of this diameter is electroplated. Plating thickness is 2 microns, I mean 2 millimeter, plus minus 0.005. Neglecting the gauge tolerance, the diameter in up to 3 decimal place. First of all, let us plot it. 25 and this is 0.01, this is 0.02, so this is 0.01 is the width of tolerance zone. So this is the pin and it is electroplated like this, electroplated. So this is 2 plus minus 0.005, 2 plus minus 0.005. But the pin is a unilateral tolerance. Because it's a tolerancing problem, all the tolerances should be like-minded. Like-minded means either equally unilateral or equally bilateral. So this is equally bilateral, this is equally bilateral. Pin also make it equally bilateral. So this is 0.005. So to shift basic size here, how much it is required? 0.01 plus 0.005. 0.015 we have to shift. So the pin will be 25.015 plus minus 0.005. Okay. Now let us go to the next page. This is the pin. This is the plating. This is also plating. And this is the overall diameter we are talking about. I just wanted to know the tolerance of the overall diameter. So first of all, basic size. Basic size will be equal to 25.015 plus 2 plus 2. So 29.015 millimeter is the basic size. 25.015 millimeter is the basic size. Now how much is the tolerances? Tolerance, you add up everything. This plus this plus this. So 0.015 tolerances. So D is nothing but 29.015 plus minus 0.015. Okay, na? Now what the question is telling you, the diameter of the go gauge, it's a shaft. So go gauge is the maximum material limit. Go gauge is the maximum material limit. Maximum material limit is upper limit. So upper limit is 29.015 plus 0.015 comes out to be 29.03 mm is the size of go gauge. If it is the size of no go gauge, it will be lower limit. 25.015 minus 0.015 comes out to be round 29. 29 millimeter will be the no-go gauge, and 29.03 will be the go gauge. Okay? Okay? Just go through once. Go and no-go plug gauges is to be designed for measuring a hole of nominal diameter 25 with a hole tolerance of 0.015, 0.015, and kindly remember that it's a hole. Consider the 10% work tolerance so gauge tolerance will be 1/10 of work tolerance. Work tolerance is 0.03. So 0.003 is the hole tolerance. It's a hole. So this will be the go gauge, and this will be the not go gauge. Point 0.003, 0.003. So I have constructed the fit diagram. Now what the question is telling you, the dimension of go plug gauge as per the unilateral tolerancing system. Unilateral tolerancing system means shift the basic size here. Shift the basic size here. So basic size will be 25 minus 0.015 comes out to be 24.985. So answer will be 24.985 plus 0.003 plus 0.00. Okay? Is that okay? So these were some of the selected questions of limits, fits, tolerances, and the gauge design. Once again, you are English speaking people. You should definitely see the questions that we have done in Abhyas, and I'm going to go forward for a very, very important topic called interferometry. Interferometry, very, very important topic for GATE exam. Very, very important topic for GATE exam, interferometry. Let us say there is one sheet. On the left hand side of the sheet, there is a source of monochromatic light. Monochromatic light is one that emits radiation of single wavelength. Radiation of single wavelength. Now there are two holes here. There are two holes, let us say O1 and O2. Through these two holes, light wave is coming out. Light wave is coming out through these two holes. Their wavelength will be same. Their wavelength will be same. Wavelength will be same. But amplitude may vary. Because amplitude depends upon how far the hole is situated from the source. How far the hole is situated from the source. So amplitude depends upon that. But because the both light waves are coming from the same source, so wavelength will be same. So the wavelength will be same. At a certain distance there is a screen. At a certain distance there is a screen, and at the center of a screen, let us say point A, at the center of the screen, let us say at point A, distance traveled by both the rays is same. Distance traveled by both the rays is same. So path difference is 0. Path difference is 0 because same distance is traveled by both the rays. So because the path difference is 0, let us say this is the wave 1, first wave. Both the waves will be in phase. Second wave, both the waves will be in phase. So as a result of that, their amplitude will multiply by 2. So this is your resulting wave. This is the resulting wave. So their amplitude, because both the waves are in phase, their amplitude will multiply by 2. This is called constructive interference. This is called constructive interference. And as a result of constructive interference, a white band will appear over the screen. A white band will appear over the screen. Constructive interference, a white band will appear over the screen. This is lambda by 2, na? Wavelength of both the light wave is same. And this is called amplitude. Correct, na? Constructive interference. Resultant of constructive interference, a white band will appear over the screen. A white band will appear over the screen. Let us say at point B, the path difference O2B minus O1B, if the path difference O2B minus O1B is lambda by 2, if the path difference is lambda by 2, this is your wave 1. So this is lambda by 2. Second wave will start exactly after lambda by 2 path difference. So this is the second wave. If the path difference is lambda by 2, both the waves will be in the opposite phase. Both the waves will be in the opposite phase. As a result of that, their amplitude will cancel. This is the resulting wave. Resulting wave will have insignificant amplitude. Because both the waves are in opposite phase, their amplitude will cancel each other. So as a result of that, you will get a dark band over the screen. You will get a dark band over the screen. Let us say at point C, if the path difference is lambda, anyway, this is called destructive interference. Destructive interference. Constructive interference, destructive interference. So at point C, if the path differences are lambda, again there will be constructive interference, so white band will appear. So white, dark, this side also, white, dark, you will get a fringe pattern. So in a summary, if the path differences are 0, lambda, 2 lambda, 3 lambda, and 4 lambda, you will get a white band. When the path differences are 0, lambda, 2 lambda, 3 lambda, 5 lambda, 4 lambda, constructive interference, and you will get a white band. But when the path differences are lambda by 2, 3 lambda by 2, 5 lambda by 2, and so on, it leads to destructive interference, and hence a dark band will appear over the screen. And a dark band will appear over the screen. 0, lambda, 2 lambda will produce white band. Lambda by 2, 3 lambda by 2, you will get a dark band. Okay, na? Now the question comes, how this concept can be used in inspection? How this concept can be used in inspection? How this concept can be used in inspection? It can be used with the help of optical flat. It can be used with the help of optical flat. See, optical flat is a disc of quartz. Optical flat is a disc of quartz. Quartz is a piezoelectric material, and piezoelectric material has got certain properties. Piezoelectric material has got certain properties. So how this technique can be used in measurement? Suppose here is the work, and L is the length of the work. L is the length of the. Please hear this very, very carefully. In interferometry, this is the most important concept. In interferometry, this is the most important concept. So for next 5 minutes, you should be highly concentrating on the topic, whatever I'm going to teach you. Put an optical flat over it. Put an optical flat over it. let us say the angle between optical flat and the work is a delta theta. Angle between the optical flat and the work is delta theta, and I would like to measure this angle. I would like to measure this angle. By the way, for your information, this angle will be in seconds. 1 degree. 1 degree is equals to 60 minutes. And 1 minute is equals to 60 seconds. So precise. So precise angle we can measure. I would like to measure this angle. So here is the source of monochromatic light. Here the source of monochromatic light. Please see very, very carefully, because many students get fumes. Okay, be little careful, because the fundamental is deep fundamental, and you know, although too many deep things I am not teaching in one shot, but problem is that without this funda you will not be able to hit questions in GATE. That is the reason I have to teach you. That is the reason I have to teach you. So let's say the light wave is coming, monochromatic light again. It will be transmitted. Now it's a property of quartz. Whatever I am going to speak, it's a property of quartz. A portion of this light wave will be reflected from the surface and come out. A portion of this light wave will be reflected from the bottom surface and come out, but a portion will be transmitted. A portion will be transmitted. This transmitted portion will be reflected from the work and come out. Transmitted portion will be reflected from the work and come out. These two light waves are nothing but bifurcation of a single wave. These two light waves are nothing but bifurcation of a single wave, but there's a path difference. How much is the path difference? A, B, C. Path difference is AB plus BC is the path difference. AB plus BC is the path difference. Because of the path difference, you will be able to see a fringe pattern over the work. Because of the path difference, you will be able to see a fringe pattern over the work. So when you are going from this side, when it is lambda by 2 dark, lambda white, 3 lambda by 2 dark, 2 lambda white, you will see a fringe pattern, because there is a path difference. Now some student asked this question, where these light waves are converging. I am looking from the top of the optical flat, so these light waves are converging on my eyes, and these light waves are converging on my eyes. These light waves are converging on my eyes. Let us say I am able to see only the n fringes. Let us say I am able to see only the n fringes. Whenever I say that I am able to see n fringes, whenever I say I am able to see n fringes, we mean to say n number of white fringes. We mean to say n number of white fringes. Whenever I say I am able to see n fringes, we mean number of white fringes. You know, when you will be able to see n number of fringes, when you will be able to see n number of fringes, the last wave that is getting reflected from the surface this one, the path difference A dash B dash plus B dash C dash, path difference should be equal to n lambda. Because I am getting the white fringe, after every lambda path difference. So I will be able to see the n number of white fringes. only when the total path difference of the last wave that is getting reflected from the work is n lambda. Is that okay? Because lambda, 2 lambda, 3 lambda, I am getting the white fringes. Whenever I say n number of fringes, it means n number of white fringes. Okay? So now the delta theta is very small. So I can say A dash B dash is approximately equal to B dash C dash, because the delta theta is very small. So can I say A dash B dash approximately n lambda by 2? A dash B dash is approximately n lambda by 2. Or can I say tan delta theta approximately equal to A dash B dash by L? Because almost be approximation, because the delta theta is very small. This divided by L is tan delta theta. Because delta theta is very small, delta theta is nothing but A dash B dash by L, and A dash B dash is n lambda by 2. So that is our formula. You know, whenever I teach these things live or offline, previously I used to teach offline for last 23 years, a student asks, "Arey sir, actually where this question comes?" I say in GATE. So after teaching certain concept, I will do 2-3 PYQ in here also. One short lecture also I will do 2-3 PYQ, so that you understand that this question appears in GATE. Okay, na? Because otherwise, why we should study these things if it is not related to GATE? Why we should study? We should not study. So this was a very, very important concept for GATE. This was a very, very important concept for GATE. Okay. Now, what is the application? What is the application? I told you that for gauges also there will be tolerance. But the variation is so low that it will be difficult to measure the tolerance on the gauges. So who measures the tolerance on the gauges? I told you optical flat. I told you optical flat. So here I can see optical flat as comparator. Once again, all of you should understand that in one shot I'm going to cover only those topics that I feel that it is important for GATE 2023, and that too short. Like the comparators, screw thread metrology in detail, and so many things we are not covering here, because I feel that an alignment test, except test also we are not covering, because I feel that one shot is the crisp that you can see in the last movement and get the full idea. That is the purpose of one shot. Okay. So there is a surface plate. And here is a master gauge. This is the master gauge. Master gauge is the one with respect to which I'm comparing the other gauges. And let us say this is the gauge that I would like to inspect. And if the variation in the height delta h, is within the tolerances, I will accept the gauge, otherwise I will throw it away. If the delta h is within my tolerances, I will accept, otherwise I will throw it away. L. And let us say there is a gap between the two gauges, and this distance is G. I would like to know what is delta h. If the delta h is within the tolerances, I will accept the gauge, otherwise I will throw it away. So do one thing, put an optical flat over it. Put an optical flat over it. After putting optical flat, you are able to observe n fringes on this slip gauge. A, B, C, D, E. If you are able to see n fringes, can I say DE is nothing but n lambda by 2? Just now I have done, na? 2 minutes before I have done this calculation. So see triangle ABC and triangle CDE. ABC and CDE. Can I say DE divided by BC is nothing but CD divided by AB? Can I do that? Check, can I do that? So D is n lambda by 2, BC is delta H that I want to measure, CD is L, and this is G. Check whether it is okay. Check whether it is okay. delta H is nothing but n lambda by 2 into G by L. So just by counting the number of fringes, I can tell you what is the difference delta H. And if the delta H is within my tolerance limit, I will accept, otherwise I will throw it away. So that's how we use the optical flat. Now, how to use these things in numericals? So here I'm discussing 3 PYQs, previous year questions, 3 PYQs. Otherwise, some teacher will say, "Arey, what you are teaching, it is not in the syllabus." If you don't know anything and if you want to teach, you just declare that it is not in syllabus. I have seen many teachers from last 23 years, certain concept they don't know. You know what they will say? It is out of syllabus. Just to scapegoat. I know the pulse of each and every one. This is the GATE question, GATE 2016. Read the question. It's a GATE 2016 question. Please read the question. And such teacher, when they declare that it is out of syllabus, they will make some tukka kind of thing and get the answer. That is not correct. It's a cheating to the students. It's a cheating to the students. 2 optically flat plates of glass are kept at a small angle theta, shown in the figure. Monochromatic light is incident vertically. If the wavelength of the light used in get a fringe spacing of 1 mm, fringe width is 1 mm, and lambda is 450 nanometer. The wavelength of light to get the fringe spacings 1.5 mm. What is W? See, here I have taught you, here, suppose over the work, if you are able to see only one fringe, over the work, if you are able to see only one fringe, n equals to 1, then the L is nothing but the fringe width. So lambda by W will be constant. Suppose there is only one fringe, then the L is equal to the fringe width. So lambda by W is constant. So lambda 1 divided by W1 is equals to lambda 2 divided by W2. So 450 divided by 1 is equals to lambda 2 divided by 1.5. Find out lambda by 2. That's the way to approach. This is a GATE question. So GATE, very beautiful question appears. Very beautiful question appears. But for that you should know the funda. You should know the funda. This is another GATE problem. This is another GATE problem. Read the problem. I think you must have seen this problem before. You must have seen this problem before. See the plan. This is the plan, na? If you see the plan here, plan will be like this. If you see the plan will be like this. But in this question, plan is like this. It means both the slip gauges are in close proximity. Both the slip gauges are in close proximity. So L is equals to G. So delta H is nothing but n lambda by 2. Directly you can put it here. So the delta H here (1.002 and 10) will it 1n 1.002. So delta H is 0.002. Delta H is 0.002, and lambda is nothing but 0.000589. If we put these things here, value of n will be 6.75. If we put all these things here, value of n will be 6.75. Value of n will be 6.75. These are the fringes on one slip gauge. These are the fringes on one slip gauge. But actually what the question is telling, see, the total number of straight fringes that can be observed on both the slip gauges. Both means here and here. So number of fringes you multiplied by 2. Number of fringes you multiplied by 2. So total fringes 2n, 13.5. Now here there is a very important point to observe here. Very important point to observe. Unless and until the fringe is complete. Unless and until the fringe is complete, we will not say it's a fringe. Even if it is 13.9, still we will say 13. Even if it is 13.9, still we will say it's 13, because unless and until fringe is complete, we will not say it's a fringe. So answer of this question was 13. Answer of this question was 13. It's a gate problem. As I told you, these things are syllabus. Some people said it's out of syllabus. Yeah, this one. Another classical problem. Check it, please. Another classical problem. Observation of two slip gauges on a flatness interferometer produce fringes counts numbering 10 and 14 for two readings. The second reading is taken by rotating the setup by 180 degree. Assume that the both faces of the slip gauges are flat and the wavelength of the radiation is 0.5086 micrometer. The parallelism error between the two faces of the slip gauges, it's a GATE 2011 problem. You know what the question is telling you about? Suppose this is the surface. This is the surface. If we are keeping the optical flat on this side, there will be some angle. N1 lambda by 2. Okay, because there will be some angle. So N1 lambda by 2. In the second setting, it says 180 degree. Optical flat is kept on this side. Because the surface is not completely flat, so there will be some angle. This is the N2 lambda by 2. N2 lambda by 2. This is the difference. Now take the mean. This is called parallelism error. Parallelism error. So n2 minus n1 lambda by 2 divide by 2. n2 lambda by 2, n1 lambda, subtract. n2 minus n lambda by 2 divided by 2 will be the parallelism error. Will be the parallelism error. So these type of question appears from interferometry. See, once again, in one shot, precision ball, sine bar, all these things I'm not touching because one shot is meant for covering the important topics for GATE 2023. So that is the reason I'm covering only the important topics that I feel. In crash course, I have touched a little more important points because time was a little more. And here for 4 hours, everything we have to wind up. That is the reason we have to take the most important topics from metrology. We have to take the most important topics from the metrology. So that was our interferometry. Interferometry. Only quick recap. In screw thread metrology, we calculate the pitch circle diameter. How to calculate pitch circle diameter? By 2-bar or 3-bar method. Here again in the crash course I went in the great detail, but I am giving you the only formula here. So one wire is kept here, another wire is kept here, and with the flat ended micrometer I am measuring this distance m. M is micrometer reading. So the pitch circle diameter will be here. This is the pitch circle diameter, and dW is the wire diameter. Only one formula you remember, diameter of wire is nothing but P by 2 sec theta. 2 theta is the angle of thread, and P is the pitch of thread. Pitch of thread means this pitch. This pitch. Pitch of thread means this pitch. So most of the questions in the GATE appears from this section. Of course, in the crash course we have gone through proofs of effective diameter and then the calculations. But if you select the most important thing, focus on wire diameter, because wire diameter calculation appeared many times in GATE. Wire diameter calculation of wire diameter appeared many times. Okay. In the last of this one-shot metrology, I want to cover a very important topic. Very important topic for GATE. This is the last topic for one-shot metrology. And in GATE, question appears very frequently from this section. And that is surface finish. Surface finish. Surface finish. So this topic I want to cover thoroughly because it is important for GATE, because those who are watching this recorded lectures, so there should be some benefit for them. If you record surface irregularities, How we record surface irregularities? With the help of an equipment called telesurf. With the help of telesurf, we record irregularities. So let us say irregularities are plotted like this. Irregularities are plotted like this. These surface irregularities can be divided into two. First is irregularities with a large wavelength. When the wavelength is large, and this is called waviness. Waviness are the irregularities of large wavelength, and the irregularities of a smaller wavelength is called roughness. Irregularities of a smaller wavelength is called roughness. How waviness appeared in the machine component? Machine vibrations, error in guideways. What is the guideways primarily we are looking for? Lead screw, that one. Chatter. What is chatter? When the tool start vibrating at a very high frequency. When the tool start vibrating at a very high frequency, this phenomena is called chatter, and the chatter leads to waviness. Then what about roughness? Roughness appears because of unexpected increase in temperature in the machining area. Unexpected increase in temperature of machining area due to improper selection of cutting parameters. What are the cutting parameters? Speed, feed, depth of cut, and so on. Due to improper selection of cutting parameters, if the temperature in the machining area increases, that leads to roughness. So roughness and waviness. Roughness. Third is a flaw. See, the roughness and waviness are repeatedly appearing on the surface, symmetrically distributed over the surface. But flaws are highly localized. Highly localized. How the flaw appears in the machined component? If you see the one-shot course of material science, that you must have seen it. In the material, there are some compounds. In the material, there is something called intermetallic impurities. Intermetallic inclusions. Intermetallic inclusions are nothing but a type of compound. So during the machining of material, when the intermetallic inclusions comes in contact with the cutting edge, intermetallic inclusion will come out, and there will be crater, and that crater is called flaw. So primarily the flaws in machining are due to appearance of intermetallic inclusions. Sometimes, let us say, there is a sudden jerk in the machine. That may also produce flaw. Sudden jerk in the machine also may produce flaw. So waviness, roughness, flaw, and the fourth thing is called lay. Lay is nothing but direction of feed. Lay is nothing but direction of feed. Lay is nothing but the direction of feed. For example, let us say there is a machined surface and the machined surface is produced by either shaping or planing. Shaping or planing, and when I'm measuring the roughness in this direction, it is called parallel lay. And when I'm measuring in this direction, it is called perpendicular lay. So both surfaces are produced by either shaping or planing, but in which direction I'm making the measurement? Parallel lay and the perpendicular lay. Okay. Suppose my surface is produced by facing operation. Surface will be like the facing operation. Surface will be produced like this. This is called circular lay. Lay, technically speaking, it's a direction of feed. Lay is a direction of feed. Suppose it's a grinding. In grinding, abrasives, they do not have any predetermined tool signature. Abrasives are oriented practically in all the possible directions. So you will not get any direction of feed. It is called multidirectional. So multidirectional lay in where you will get when we are grinding the workpieces. Let us say if it's a knurling operation. So we are making like this. It is called crossed. It is called crossed lay. Now let us say you are performing the slotting operation. You are performing the slotting operation. Slotting operations are performed to make the keyways notch. So the direction of feed will be radial. Direction of feed will be radial because I'm moving the cutting tool towards the center to cut the keyways. So anyway, you can think over the other ways also. Just I have given you some example that how the lay is defined. How the lay is defined. Okay. Now how to do the measurements? How to do the measurements? Measurement of surface finish. How to do the measurement of surface finish? How to do the measurements of surface finish? First of all, you have to establish the datum. You have to establish the datum. There are two different ways by which we can establish the datum. There are two different ways by which we can establish the datum. There are two different ways by which we can establish the datum. First is M system. M stands for mean line. M stands for mean line. So you are plotting the surface irregularities. You are plotting the surface irregularities after plotting the surface irregularity. You join the first and the last point to get a reference line. To get a reference line, this line is shifted in the vertical or downward direction. This line is shifted in the vertical or downward direction to the point so that the area above the line and area below the line are same. Area above the line and area below the line are same. Now this line is called mean line. In India we follow this system because Britishers used to follow this system. And when India got independence, our Prime Minister Nehruji, he brought the British system as the Indian system. Now second system is the E system. And E stands for envelope. E stands for envelope. So how we do it? After plotting the surface characteristic, one sphere of 25 millimeter diameter, is rolled over it, and the locus of its center is being traced. Locus of its center is being traced, called envelope. In Abhyas batch, we have done some problems based on that. Some difficult Abhyas batch, we have did a lot of difficult problems. So all of you, if you have time, please see those Abhyas batch questions, because it's all new questions, difficult questions. Okay, we have done it. Now shift the envelope in the downward direction. Shift the envelope to the downward direction till the area above and the area below are same. And this is called mean envelope. It is called mean envelope, and the measurements are taken from this mean envelope. Technically speaking, it's a better system, and US they follow this system. You know why? Because E system eliminates waviness from the measurement. It eliminates waviness from the measurement. See, you want to take decision to improve the surface. You want to take some decision. But first of all, you should know that whether it's a roughness or a waviness, only then you can take some decision. Nah? You should know that whether it's a roughness or waviness, only then you can take some decision. So E system eliminates waviness from the measurement. Is that okay with everyone? There are two different methods by which we can establish datum. Next, quantify. Quantify roughness. Of course, there are 6 or 7 different methods to quantify roughness. But for examination point of view, 4 are important. Peak to valley height, peak to valley height. It is represented by RT, Hmax or Rmax. You have to know actually what is the symbol. You have to know that. Peak to valley height is, suppose this is the characteristic of surface. Peak to valley height is difference between highest peak and deepest valley. Peak to valley height is difference between highest peak and deepest valley. Difference between highest peak and deepest valley. So it's an easy one. Second is central and average value. It is represented by CLA or RA. Represented by CLA or RA. Here you should look little carefully. Next 10 minutes. Next 10 minutes, please hear carefully. Next 10 minutes. Suppose this is the geometry and this is the mean line. So take number of points y1, y2, y3, y4 and just take the average. y1 plus y2 plus y3 . Many students ask this question that when we are taking the points below, it should be negative? No, it should be positive. Even though we are taking the points below, but still it should be positive. Once again, now onwards, I will repeat the things 2-3 times because for GATE it is very, very important. You are taking the points above or below. Above or below, even though you are taking point below, still it should be taken as positive, not negative. Still it should be taken as positive, not negative. And RA value is approximately Hmax by 4. Hmax is the peak to valley height, na? This formula don't apply blindly. This formula do not apply blindly. This formula do not apply blindly. Do not apply blindly. If the number of hills and number of valleys are given to you, if number of hills and number of valleys are given to you, don't apply this formula. What I am saying, suppose it is like this. These are all GATE questions. 20 peaks, 20 valleys, 5 micron, 5 micron. So what is the peak to valley height? 10 microns, na? Peak to valley height is 10 microns. Now let us see what is RA. I will go by the first principle. 20 peaks of 5 micron, 20 peaks of 5 micron valley, and how many total observation? 40. So answer is, see, it is not 4 times. See, it is not 4 times. So once again, when number of hills and number of valleys are given to you, do not apply this blindly. Do not apply this blindly. Do not apply this blindly. Suppose it is like this. Ten peaks of 5 micron, 5 valleys of 2 micron. This type of question also may appear. So CLA is nothing but 10 into 5 plus 5 into 2. How many total observation? 5 and 10, 15. That way we will calculate. Once again, when the number of peaks and number of valleys are given to you, I will count it and then do it. I will not apply this 𝐻𝐚𝐴𝑋 by 4 formula blindly. I will not apply this 𝐻𝐴𝑋 by 4 formula blindly. When number of peaks and number of valleys are not given to you, then you apply the formula. Okay, na? The CLA value can be integral 0 to L y dx mod y dx. There also we can do it. Suppose the profile is given to you. Suppose the profile is given to you, you can do like that. For example, suppose there is a sinusoidal curve. So how to find out the CLA value? 0, pi, 2 pi, na? So these curves are same. So integrate only this much. All right. Let us say L is the cutoff length. Area above the line is sigma A, and area below the line is sigma B. Kindly note that if it is a mean line, you have to see very, very carefully. If the line is a mean line, summation A and summation B will be same. If it's a mean line, summation A and summation B will be same. But suppose you have drawn the mean line for this sample, but you would like to know the CLA value for the smaller sample. You have calculated a mean line for this sample, but you would like to know the CLA value for a smaller sample. Summation A and summation B will be different. And in this case, CLA value will be summation A plus summation B divided by L. Here you should know that if the vertical and horizontal magnifications are given to you in the question, if the horizontal and vertical magnification are given to you, you have to divide. Magnification, you have to divide. If the horizontal and vertical magnifications are given to you, you have to divide. Okay, na? Total area, both above or below, divide by the cutoff length. Now, there are some beautiful problems that appears. There are some beautiful problem that appears. This is gate problem. 30 degree. Ten micron, 10 micron, 5, 10. From here the geometry is repeating. You have to find out CLA value. These type of problems appears in gate. Here, remember one funda. Remember one funda here. Funda is, you have to consider the geometry. Funda is, you have to consider the geometry from wherever the geometry is repeating. From wherever geometry is repeating. See, the geometry is repeating from here. Geometry is repeating from here. This is the cutoff length. So L will be how much? 10 plus 5, 15 microns. So CLA value will be within that L. Within that L, how much is the area, both above or below, divided by that L, meaning 10 by 10 divided by 15. So 100 by 15 microns. So 6.67 microns is the CLA value. 6.67 microns is the CLA value. Little more variation. Ten, 10, 10, 5, 10, 10. All are microns. And the same geometry keeps on repeating. Now what will be? What will be CLA? Now from here the geometry is repeating. This is L. So L will be 14 microns. And the total area will be 10 into 10 plus 5 into 10. 100 plus 50, 150. So CLA value is nothing but 150 divided by 40. So once again, you have to identify from where the geometry is repeating. That becomes the cutoff length, and within the cutoff length, whatever is the area, both above or below, calculate the total area, divide by the cutoff length, you will get the CLA value. You will get the CLA value. It is very, very important. It is very, very important. When the tool signature is given to you, like back rake angle, side rake angle, end relief angle, side relief angle, end cutting edge angle, side cutting edge angle, and the nose radius. Nose radius. This is called psi. This is called psi 1. Okay. So Hmax is nothing but F divided by 10 psi plus cot psi 1. And here for CLA is Smax by 4. So this formula we will apply when the complete tool signature is given to you, and when the feed and the nose radius is given to you. Complete tool signature is not given to you. Complete tool signature is not given to you. Only the feed and nose radius is given to you. Then Hmax will be f square by 8r. So you have to be very, very careful in handling CLA questions. So I have discussed summary. You have to be very, very careful in handling the questions related to CLA value. Now next is central and root mean square value. First was peak to valley height. Second is central and average value. Third is root mean square value. RMS value is also called RG. It is also called RG. Root of mean of square. Y1, Y2, Y3. So RG is nothing but root of mean of square. Y1 square plus Y2 square plus Yn square divided by n. Root of mean of square. Okay. And finally, there's a 10-point value. And the 10-point value is represented by RZ. 10-point value is represented by RZ. What is this RZ? What is this RZ? It is the average of 5 highest peaks and 5 deepest valleys. It's the average of 5 highest peaks and 5 deepest valleys. Peak to valley height, central and average value, root mean square value, and the 10-point value. Of course, there are other methods like bearing curves and all that, but I have not seen any question appearing in gate from bearing curves and other things. That's the reason I'm not incorporating. So in this one-shot course of metrology, what I have discussed, some of the most important topics that I felt is important for GATE 2023. This evaluation was based on looking at the previous year questions and IIT Kanpur, the previous questions of IIT Kanpur, because this year 2023 will be set by IIT Kanpur. So based on that, our team Drona, they have evaluated, and accordingly certain topics they have incorporated into, first of all, crash course. Crash course was little elaborate. One shot is condensed nectar. So that's what I wish to give you in metrology. There are other lectures on forming and casting that I will take up later. Thank you very much.